Welcome back. So we're talking about the divergence, the gradient, and the curl, these vector calculus operations that we're going to use to describe physical systems and partial differential equations. In the last lecture, we talked about the gradient operator, and now we're going to zoom into the divergence operator. And this one is really, really useful for studying things like fluid flows, compressible or incompressible fluid flows, and a lot of other applications to the divergence. So I'm going to jump right in. Remember that this nabla or del operator, if I write down del in 2 dimensions, that is a vector of partial derivatives, partial x, and partial y in the second component. So it's a 2-component vector field. The first component is a derivative in the x direction. The second component is a derivative in the y direction. And the gradient would apply this del operator to a scalar function f, which would then create a vector-valued function of the partial derivatives. But the divergence, notice we're taking the dot product of this vector of partials. And so we're going to take the dot product with a vector-valued function f. So if we have some vector-valued function f, we'll call it f bar. And we'll say that that has components f1 and f2. And in general, f1 would be a function of x and y, and f2 would be a function of x and y. I might drop this dependence in a little bit. Then we can take the divergence of f, or the del dot f, just like you would normally do a dot product of 2 vectors. This is a vector, and this is a vector. And so if I take, sometimes we call this div for the divergence of f. And that equals del dot f. And that equals the partial x of f1. So partial f1 partial x plus partial y of f2 plus partial f2 partial y. Now remember, when I had a scalar function, just a single scalar function of x and y, if I took its gradient, I created a vector-valued function. And similarly with the divergence, if I take the dot product of del with a vector-valued function, the dot product of 2 vectors is a scalar. And so I take my vector-valued function, and its divergence is a scalar-valued function. This is just a scalar function, which is the sum of these 2 partial derivatives. Okay? And this is really, really useful. This essentially, I'll show you in pictures in a minute, in some examples. This quantity here tells you how much that vector field f, this f is a vector field, it tells you how much that vector field is locally sourcing out or sinking in, kind of pulling material in or blowing material out. And if the divergence is 0, then there's no net kind of local compression or compressibility of that vector field. So we'll talk about this in a little bit. I want to point out, just like the gradient operator is a linear operator, the divergence is also a linear operator. So maybe I'll just write that out very, very explicitly. So div is linear. And what this means is that if I take the divergence of the sum of 2 vector fields, f, let's call it A plus f b, that equals the divergence of fa plus the divergence of fb, and so on and so forth. So you can verify this yourself, kind of just try this out, and you'll see that this definitely does add in a linear way. Similarly, the divergence of a constant times fa is just that constant times the divergence of fa. And so this operator is linear, which means that the sum of solutions is also a solution, which is kind of nice. So we're going to use these as building blocks for partial differential equations later. And those PDEs, if we build them out of these building blocks, will be linear partial differential equations. Okay, good. So I want to give you some examples of this divergence, just to give you some intuition for what this means physically. So I have 3 examples I'm going to walk you through. And those 3 examples are pretty simple. So here's what I'm going to do. Let's write down the vector field for example 1. So example 1, we're going to have our vector field f of x and y is going to equal x in the I direction plus y in the j direction. So this is, I'm just going to write these in lots of different ways so you get comfortable going back and forth between this kind of unit vector notation or this column vector notation. So similarly, this would be written as x and y. Okay, that's what I mean to have x in the I direction and y in the j direction. It's a vector like this. And so what that means is that at every point x and y, there is a vector of magnitude and direction given by this vector here. So let's actually draw this out. So if I look at the xy coordinates, then what I can do is at every point x and y, I can draw the vector given by this vector field. So at the x equals 1, y equals 0 point right here, there is a vector pointing in the 1, 0 direction, so like this. Similarly, in the 0, 1 direction, there's a vector pointing up. In the negative 1 direction, pointing out, and so on and so forth. At the 1, 1 point, I have a vector that is 1, 1, so going in the x and the y direction. And it looks kind of like this. So you get this idea that everything's kind of moving out away from the origin in this. And so our intuition is that the divergence of this vector field should be positive because things are diverging away from the origin. So let's actually compute this divergence here. So we'll compute div of f. The divergence of f is equal to partial f1 partial x, that's just 1, plus partial f2 partial y, that's also 1. So this is like partial x plus partial y equals 1 plus 1 equals 2. So what we say is that this flow has a positive divergence, or the flow is diverging. That's kind of how we would say it. This flow is diverging. And another way to think about this is that if I had a little blob of, a little patch of material here, and this was a fluid flow in the ocean, this is a little oil slick, and this is the fluid flow in the ocean, then if I integrate that patch of particles forward in time, I flow it along the fluid flow, that patch is going to get bigger by a certain amount. And it's in fact going to get bigger in an amount that's related to the divergence. Okay, so a positive divergence means that little patches are locally going to get bigger or kind of expand. And a negative divergence would mean the opposite. Patches are going to contract or shrink. Okay, so you can think of this like a little point oil spill, and things are going to source out from that. Okay, let's do another example. So the other example I want to do is kind of the exact opposite case where we have a converging or negative divergence vector field. So we'll have the same f x and y equals, and now in this case we're going to say it equals minus x in the I direction, minus y in the j direction. And so we've literally, all we've done is changed all of the arrows, all of the directions of these arrows. So now my points are moving in a way that is kind of proportional to x and y at those points. And again, if I'm farther out, if I'm at -2, -2, then my point is moving in even faster. And so that's also important to draw, that these are kind of from farther away, they actually accelerate in. Okay, good. So let's, again, go through the motions of computing this divergence. I just want you to get very comfortable doing these vector operations. So the divergence is just the dot product of this partial derivative vector with this vector field f1, f2. And so let's do that. The divergence of f in this case is, again, partial minus x partial x. So partial minus x with respect to x plus partial minus y with respect to y. And that equals -1 plus -1 equals -2. Maybe I'll box these. Okay, and so in this case, essentially, if we just change the direction of our vector field, so instead of everything kind of blowing out, things are sinking in, I have a negative divergence, and we say that this flow is converging. So this one was diverging, and this one is converging, okay? Or it's a compressible flow. Things are compressing. And again, if I take my little patch, now I'm going to start with a patch kind of out here. I have a big patch, And if I flow that big patch forward in time, it's going to shrink by a factor that's related to this divergence, this -2 here. Okay, so that's really, really useful. This kind of divergence being positive means our volumes grow. Divergence negative means our volumes contract. And for the last example, I'm going to show you a vector field that has divergence 0. And we'll see that the kind of volume of these patches stays the same. So that's the third example. Example 3 is a flow with divergence 0. Maybe I'm giving away the punchline. So this vector field, I think it's going to be minus y in the I direction plus x in the j direction. So this one's a little different than these. In these vector fields, the x component was equal to x and the y component was equal to y. But here they're kind of switched. So this equals minus y x. And now I'm going to draw this vector field here. So again, if I want to draw this vector field given by f arrow, I literally just take test points and I evaluate what is this vector at all of those test points. So at the 1, 0 point, when x is 1 and y is 0, this vector is 0, 1, which points up. So right here, my vector field is pointing up. In the 0, 1 position, when x is 0 and y is 1, this is a -1, 0 vector. So it's pointing in the left direction, -1 in the x direction, 0 in the y direction, and so on and so forth. If I'm here, it's pointing down. If I'm here, it's pointing to the right. If I'm farther out, it's twice as big, so I get this kind of thing going on here. It's a little hard to draw these. If I'm at some diagonal point here, it's kind of moving diagonally like this. So that's what this flow looks like. And we'll compute the divergence of this to confirm that it's 0, and then we'll drop our test patch and see what happens to that test patch. Okay, so the divergence of f is equal to partial f1 partial x, so that is partial -y with respect to x, plus partial f2, which is x, with respect to y. And now, partial y with respect to x is 0, partial x with respect to y is 0, and so this vector field has 0 divergence. It is divergence free. I'm going to write that down. So this is called a divergence free vector field. Okay, very important type of vector field. And one of the kind of intuitive pieces is that a divergence-free vector field is characterized entirely by rotation. So it's not sourcing or sinking, it's only rotating. And so again, if I take my little patch here, let's put a little patch right here, this patch doesn't get stretched or shrinks, it just rotates around. This flow literally just kind of is a solid body rotation, and it just, after some amount of time, moves that patch so it stays the same, but rotates over. Okay? And so this is a nice example of a divergence-free vector field. So this one has positive divergence, this one has negative divergence, and this one has divergence-free. Okay, good. So those are 3 examples of the divergence. There's a couple things I want to show you here because I think this is really, really useful, is that when I have a vector field like this f arrow, you can think of these vector fields as establishing a differential equation. So this differential equation here, if I take this f bar of x and y, let's just rewrite this as a differential equation. So what I can do is I can think of how a particle will flow or move around in this vector field. And this is a very useful perspective in systems. So I can write ddt of my point xy equals f bar of x and y. And in that case, it equals this vector field here. So in matrix notation, it would be 1, 0, 0, 1 times x and y. Okay, and we're used to seeing this kind of linear systems of equations from differential equations. So that's one way you can think of these vector fields. These vector fields are essentially the right-hand side of a differential equation for what a particle would do in that vector field. So this field of vectors, if I drop my little red particle or pink particle here, I can integrate this differential equation to find out where it goes. And then here, of course, you see that the solution is going to be x, maybe I'll just write it down here, x and y at time t is going to equal e to the t times x naught and e to the t times y naught. And so you kind of have this, this growth of these initial conditions. They expand and they accelerate away from that initial condition. Okay, good. And maybe what I'll do in a future lecture is I'll relate this quantity, this divergence quantity, to kind of these exponential expansion of particles, because there's a rigorous way of connecting this divergence quantity and kind of the exponential expansion rate of particles in these vector fields. Okay, let's just recap. So we're talking about the divergence, which is the dot product of my del or nabla operator with a vector valued function. And again, when I take the dot product of two vectors, I get a scalar. So the divergence of a vector valued function is a scalar function. It's just a scalar. In this case, it was a constant because my vector field was linear. If I made this an x squared here, then this would be partial minus x squared partial x would be minus 2x minus 1. And the divergence would actually be a function of x. So but it's still a scalar function. It's not a vector function. It's a scalar function of x and y. And it can quantify locally in my vector field, is my particle expanding, is it contracting, or is it just doing kind of a solid body rotation with divergence free? Now, the last thing I want to show you is what happens if I take a scalar function. So remember, I can take the gradient of a scalar function. So I can take my regular old scalar function f, and if I take the gradient of it, now I have a vector valued function. So this would be a vector function partial f1 partial x, partial f2 partial x. And so what if I take the divergence of the gradient? So if I take the divergence of the gradient of a function f, then essentially what this equals is partial x, partial y, dot product with partial f, sorry, this is just f, because this is a scalar. I really botched this up. Pardon me. This is partial f partial x and partial f partial y, because f is a scalar, and so this is the gradient. Partial f partial x, partial f partial y. And if I compute this dot product, remember the dot product of two vectors is easy. You just take the product of the first two, the first components of both of them plus the product of the second components of both of them. And now what I have is the second partial derivative of f with respect to x squared plus the second partial derivative of f with respect to y squared. So this is cool. This is the sum of second partial derivatives of f with respect to x and y. And so the divergence of the gradient of a scalar function f is this quantity. This is called the Laplacian of f. This is del squared of f, and it's also a scalar value, the Laplacian. And this is going to come up all over the place. This is one of the most important linear differential operators in all of physics. This is how we're going to study electrostatic potentials, incompressible irrotational fluid flows. This is an extremely, extremely important quantity I'll tell you all about later, kind of how to work partial differential equations using this operator. But again, I just want you to be very comfortable that you can use these building blocks together. If I have a scalar function, I can compute its gradient to get a vector function. If I then take that vector valued function, I can compute the divergence of it to get another scalar valued function. And that scalar valued function, the div of the grad of f, is called the Laplacian, and it's a very, very useful, useful quantity. Okay, so I hope you're finding this interesting. We're about to, so I'll tell you about curl next time. Kind of, we'll actually look at this example down here where this field is divergence free, but it's rotating. So we'll compute the curl next time. Then we're going to start talking about some kind of identities like Gauss's theorem, Stokes's theorem, and how you can use these building blocks to build partial differential equations. For example, Laplace's equation. What happens if I say del squared f equals 0? This is a partial differential equation. It's a differential equation with partial derivatives. And the properties of f will be a very, very special function if it satisfies this partial differential equation. So that's all coming up soon. Stay tuned, and you're going to know, tons about PDEs and vector calculus in a few more lectures. Thank you.